What I'm going to do in this video is make a mains inverter. I've lived off the grid for about 30 years now, and periodically we do have a problem with our inverters. Quite simply, they blow up, and when they do so, they do it quite spectacularly, like burst into flames. There's nothing unusual. To buy a new one is going to set me back a pretty penny, and I thought, well, why can't I make one? So I'm going to set out to design a mains inverter that runs off 12, a universal mains inverter that will run off 12 volt, 24 volt and 36 volt. So let's write down a list of what we want: 24, 12, 24, 36 volts input. Second thing we need, and this is most important, is a very low standby current. So I'm going to try and go for 20 milliamps or less standby current. We always need a list of specifications before we design something. Now if we're going to go to all this trouble, and it turned out not to be much trouble at all, let's go for a decent amount of current. So we'll go for, say, 1.5 kilowatts at a 12 volt input, because here we're looking at about, oh god, I don't know, 120, 130 amps. It's probably about the realistic maximum for a 12 volt battery bank, because yeah, that's one hell of a lot of current. If we go to 24 volt, we can actually, with the same FETs and circuitry, we could do 3 kilowatt at the same current. So we'll make that 24 volt. What other things do we need with this inverter? We need temperature protection, so a sustained long-term current draw, not necessarily an overload, but sustained long-term current draw may just overheat it. So we want temperature protection. We want it to shut down automatically if it goes over temp. We need voltage regulation. Yeah, we don't want it to go to, I don't know, 400 volts. We're a 240 volt 50 hertz supply here, so we don't want it to go over 300 volts or below, I don't know, 200 without wrecking stuff. So yes, voltage regulator, very important. We want absolutely true sine wave. You know, if we're going to mess around making one of these, let's make a sine wave one. It's got to use easily available parts, so you know, available parts. Don't want anything fancy in this. It's got to be cheap to make. Hopefully we'll use the parts I've already got here. And simple and cheap go together. And reliable. The beauty of making your own inverter, of course, is if you've gone to all the trouble of making it, you know the thing intimately, in which case you won't have any trouble fixing it. And I want this one to be universal. I want it to be one control circuit. Universal. I want it to be one control circuit that will be able to be built up and used in any power output stage. So for argument's sake, the same front end will run a 100 watt inverter with just a couple of high current FETs, or the same control unit can do a 1.5 kilowatt inverter. So it's cheap enough to make. This could be just like a simple sub-assembly. Yes, so that's our list of wants with this thing. I can't think of anything else. But that's pretty much the important parts of a good inverter. We want overload protection. We haven't got overload protection, so let's add overload protection. In case we short the output out at some stage, or if the appliance that's plugged into it goes faulty. what else? Can't think of anything else here. Let's put a price on this thing. Now to buy a 1.5 to 3 kilowatt inverter, pure sine wave inverter, costs you an absolute bloody fortune. So let's put a price on it. I don't know, what's a good price? $50. Cheap and simple, $50. There we go. There's the challenge, to build it 50 bucks. Can we do it? Well, I think we can. Now I've had a bit of a play, well not a play, well yes a play and a think over the last few days. I've had a scrummage through my myriad boxes of stuff and I've actually come up with a design. Now before we get into that, let's discuss inverters. There's two main types of inverter. There's the don't waste paper. There is the high frequency two-stage inverter. This encompasses most inverters you buy, especially Chinese ones. They use a couple of FETs into a high frequency transformer, and these are gated on and off at, I don't know, something like 30 kilohertz. I'm not sure what frequency they use. But these are high frequencies simply and purely to use smallish transformers. These are little, usually yellow for some reason, yellow ferrite transformers. Only about a couple inches square, they're not very big at all, and this is the main reason why they use high frequency. The output of that is rectified, just like that, and goes into filter caps. So here we have sitting on here, for our mains at 240 volt, we have about 350 volts DC on here. For you 120 volt countries, you would have, well, I don't know what you'd have, 170 maybe? 170 volts DC. Now this is what I call the first stage of the inversion process. High frequency inverter, simply chopping the battery voltage, 12, 24, 36 volts, whatever it happens to be, chopping it up into a high frequency, passing it through a transformer, rectifying it into 350 or 170 volt DC. The second stage of the operation is that they feed this voltage back into a couple of, couple of choppers, which are then fed with your AC mains frequency. So that could be 50 Hertz, or it could be 60 Hertz, wherever you live. And this outputs a square wave to the output terminals of the inverter, 250 or 120 volt square wave, peak to peak. They generally put in an inductor, series inductor into the leads here to try and compensate for the square waves round the edges off, whatever you like, so they call it a, well, wishful thinking, call it a sine wave inverter. Now the problem with these inverters is that the first thing that blows up on them are these input FETs. They are really stressed. The FETs are a pain in the arse thing to drive. The gate, the millicapacitance in the gate, they basically have a capacitance between here and here, and they take an awful lot of current pushed in and out of the gates to turn these things on and off. The higher the frequency, the more current's needed to push these gates or push the FETs into full conduction. If they're not into full conduction, they're just going to blow up. That's the first problem with these things. The second problem is manufacturers making these things, they leave out all the protection circuitry. Manufacturers won't put anything into an appliance that is of no immediate benefit to the user. So the most you hope for is a fuse. Now everyone into electronics knows that a fuse is the last thing to blow. The semiconductors actually protect the fuse, not the other way around. The only thing a fuse does is arguably to prevent fire. When these things blow up, they usually short the FETs. They've got the full 12 volt or 24 volt current, which could literally be hundreds of amps flowing through a shorted FET, through a circuit board trace, through another FET, back to ground. So consequently, there is a really good possibility that the circuit board is going to catch, and I've had this circuit board's catching fire. So the fuse actually protects from fire damage. It doesn't protect the circuit at all. It's a pathetic way of trying to put any overload current protection in it all. But you get what you pay for. The other problems we have with these is you know, well, I won't go into it because I'm not even going to worry about dealing with anything like that. We're not going to make one of them. I'll tell you that now. The second way of doing an inverter, and this is the age-old method, and this is not done with manufacturers much anymore because they can use a very expensive component, an old-fashioned component invented way back in Faraday's time. It's called a transformer. However, the low frequency method of doing this does the voltage and frequency conversion all in one step. We basically have a centre tap transformer, we have a couple of FETs, same topology really as we've had before. We feed in 12 volts in here, or 24, and we have our secondary 240 volts AC, 50 Hertz, or 120 volts AC, 60 Hertz. The gates of the FET are simply fed with out of phase signals to turn them hard on and hard off, and this is done through a series of a signal. So when that one's high, that one's low, so, and there's always a gap between the two so they don't come on together. This is the age-old method. As you can see, we do everything in one go. We feed an oscillator into here, and pretty much that's all we have. So that runs at 50 Hertz, 50, 60 Hertz. The whole system runs at 50, 60 Hertz. That is a dead simple way of doing it, and this is a method we're going to use today. The other good thing with the high frequency inverters, the amount of capacitance in the FETs is amplified by the frequency. The higher you try and push frequency, you try and push these things, the worse this Miller capacitance gets. At 50 cycles it's still there. We can use upwards of half an amp to an amp just to turn one FET on and off very quickly. We've still got to turn them on quickly with this. But because the commutation time is now just a very small part of the total conduction time, it's not as critical. It's nowhere near as critical as it was in the high frequency design. Manufacturers hate transformers. Transformers are expensive components and are labour intensive to make. You've got all the stampings, you've got the coil winding, which generally is a mechanical operation, but I'm pretty sure it still has to be done with operators. You know, have to start and finish the windings and stuff like that. So yeah, manufacturers don't like stuff that employs staff. A pack of greedy capitalistic bastards actually that would ideally like a factory that never breaks down, doesn't employ anybody, and just runs on machines that work 24 hours 7 days a week and just require a little bit of oil periodically. That's what manufacturers want. So that's what we're going to do. So a little bit of thought, I have decided to build this, and this is the circuit diagram. You upside down there? No, you're not. Okay. Now this uses less than, I don't know, I'd say about $5 worth of parts. Seriously, there is bugger all in it. And it contains all the things we wrote down here. Let's refer back to this. I'll add another one in here too. We have 50, 60 Hertz selectable, fact, you can adjust it to any frequency you like. It probably run from 20 Hz up to about 150. So you can use it to speed control induction motors, for instance. We can also make it 120 volt or 240 volt output. Obviously with 120 volt the current's twice what it would be at 240 volt, but the wattage remains the same. So 3 kilowatts at, or 1.5 kilowatts at 120 volts is still 140. Oh shit! I must be tired. Forget that. However, let's study the circuit here. I'll get a bit of paper so I can block off the irrelevant bits. I saw someone else on YouTube do this. It's actually quite a good idea. So let's get rid of half the circuit. No, not quite half the circuit. We need that bit there. So here we have. Can I zoom that in a little bit? Oh, I don't know how to work this bloody thing. Bugger it, leave it alone. Okay, here we have an oscillator. Now this is probably the simplest oscillator you can do. Incidentally, all this uses is bog standard 4000 series CMOS chips, 3 of them, and an LM311 comparator, a 4093 hex quad SMIT NAND gate, and a handful of transistors. That's all we need to do this. Now, the simplest oscillator in the world, we tie 2 gates of a hex SMIT NAND gate together. We bias it with a resistor and we hang a capacitor to ground. That is an oscillator. The frequency is determined by value of R and the value of C. And how this works is quite simple. It's called a relaxation oscillator. Relaxation. If you can read more. When you first turn the circuit on, when you first apply voltage to this, that capacitor is discharged. This is inverting, so if the input is low, the output will be high. So therefore, current flows through the resistor and starts charging the capacitor up. When the capacitor gets to roughly 2/3 or 1/3 supply, is it 1/3? 2/3. 1/3 supply, this will change state. So then it will start dragging current back out of the capacitor that way, because that's gone low because this is high. And this will keep doing this till the cows come home. This is a quickie oscillator, and this is what we use here. There's the oscillator there, and for 50 Hertz operation, which the oscillator isn't running at 50 Hertz, it's actually running at 800 Hertz. The reason for this will become clear shortly. So to get the correct 50 Hertz frequency or 60 Hertz, we need a frequency here of 800 cycles, CPS, for 50 Hertz, and a few more cycles for 60 Hertz. What's 8 times 6? 4, 8. I think it's 960. I'd have to work it out. But anyway, well, this is encompassed in the range. We actually make this resistor variable so we can fine tune it to get the frequency, the exact frequency we want. So the oscillator frequency is a square wave. It comes up and it clocks the first 4013. Now a 4013 is simply just a divide by 2. It's actually a dual data flip-flop. And the beauty of these things is that not only do they divide a signal by 2, but they have complementary outputs. Complementary outputs. So when one is high in voltage, so if that one's high, that one will be low. And they cannot overlap. So this is exactly what we need to trigger our gates of our FETs. So here we have the first 4013 here. It's driven by the oscillator which goes into pin 3, and it's cascaded with the second flip-flop in the package, because there's 2 flip-flops in each package. And the output of the second flip-flop, we've divided the 800 now. First flip-flop divided it down to 400 cycles. Now we're down to 200 cycles. That goes into third flip-flop, which divides it down to 100 cycles. And the last one divides it down into 50 cycles for our mains frequency. Now why we do this is because in order to get a sine wave inverter, we need synchronized pulses so that everything runs in unison. We can't have 2 free running oscillators, they'll get out of sync and cause mayhem. Now these are 4093 NAND gates, Smith NAND gates. A NAND gate, if you don't know, is a gate that will take input A and input B and the Q output. So we end up with a truth table for these things. You'll see these in data books. So we've got A, B, Q. So if A is low and B is low, so no voltage there, no voltage there, Q is high, the output will be high. If we have A high and B low, the output will be high. If we have A low and B high, the output will be high. When we have a high and a high, i.e. they're both high, this will go low. This is called ending. It'll only go low if both inputs are high. A and B is high, then Q will be low. So these are quite handy because we can feed a signal in here, which we do in our inverter circuit. We feed our 50 Hz into this pin. By taking this pin high, it will appear out here. By taking that low, that one there will just sit high at a high level. It won't toggle, won't do anything. So this allows us to combine 2 signals. So let's call it a combiner. So here we see them here. We've got one for each channel. We've got one for the high FETs, one or the top part of the half sine, and we've got one for the bottom half of the sine. We configure the sines in 2 halves so we can modulate them accordingly. These here are just a couple of PNP transistors, NPN transistors. These here set up the conditions for driving the FETs. Now these are driven by a Zener diode regulated supply. Some FETs have a turn on voltage of 5 volts onto the gate. Some may require 10 volts, some even more than that. So we don't want to exceed that level, so this Zener limits the high the voltage that can appear on these collectors when these transistors are turned off. It's probably not a best way of doing it, but it's good enough for what we want at the moment. And the other thing too, using transistor buffers on this board is simply to protect the digital stuff, which is CMOS, and it's quite voltage sensitive, spike sensitive. So put a bit of isolation between them and the real world. So that's basically the guts of the inverter. In fact, that on its own, just that bit there, would work as a square wave inverter, and that would be fine. Now, how do we get a sine wave of this thing? Well, let's have a look here. On this capacitor, getting back to this capacitor, the charging on this would look something like this. So it charges up, it discharges, charges up and discharges. Now the way these gates are made, they don't toggle at exactly half rail. If we've got a 9 volt rail, the threshold point, we have 3 volts, 6 volts and 9 volts. Oh, I've got it back to front, haven't I? We've got 9 volts, 6 volts, 3 volts and 0 volts. So the first threshold point is at 3 volts. That's when it will turn on. So as the voltage rises, it'll turn on there. It'll turn on there, and the voltage continues to rise, but when it does so, it'll turn off there. So we've got this what's called a band gap. No matter what the signal does in this area, the output won't change. This is directly a result of the high noise immunity of CMOS chips. So our waveform is going to have a peak voltage of 3 volts. 3 volts, peak to peak. So we feed that into one side of a comparator, differential comparator. Well, all comparators are differential. It's hard to explain otherwise. And the way a comparator works, it compares one input to the other input. So on this input we're going to feed this signal. And on this input we're going to feed a divided down signal. And we take it from the 100. So this is happening at 800 cycles. And we're going to feed a similar signal at 100 cycles. Now, I'll draw a diagram here. I'll show you on the scope shortly. There's one. This is how we get a pulse width. There's our 800 cycle signal. And 1, 2, 3, 4, 5, 6, 7, 8. Look at that. And here is our 100 cycle signal. It's the same. Oh, and that slides off back down. So I'll continue that. That's number 8, number 9. Now our comparator looks at these points. So this is on one input, this signal's on the other input. So let's draw in the 0 crossings here, or where both signals coincide. This is pulse width modulation 101. Oh, I've cocked up there, haven't I? I missed one out there. And what do we have? Look at this. Look what we have here. We have pulse width modulation. So we have very wide, less wide, less wide, less wide, less wide, less wide, less wide. This signal then, the square wave signal, now becomes the output of the 311. Now, as we've already established, we can modulate this waveform with this waveform. We can combine the two together, and the net result is a waveform coming out of one of these which looks something like this. So we want a narrow one that's slightly wider, one that's slightly wider, one that's slightly wider. 1, 2, 3, 4, 5, 7, 8. And that is encompassed in our 50 Hertz half cycle. Now, if we integrate this and look at the, I don't know, say the average level of each of these boxes, you know, we know that this is a lot of voltage sitting in these, so we're at the point of the waveform there. This here's got approximately half the value, so that'll be down there. I'm just guessing this, as you can see. This has got even less, so the voltage will be less, the average voltage level. It's basically the area under a curve until it falls down to the 0 point. So here we have a PWM rendition of a sine wave. We're actually not using a sine wave, as you can see. We're using a sine wave would look more like that, but we're using a triangle wave, which is near enough. A triangle wave is better than a square wave for poking through transformers. And transformers, being the little handy little buggers they are, they'll actually integrate this into a sine wave. These steps are occurring at 800 Hertz. So consequently, the transformer can't process 800 cycles as good as it can with a 50 cycle waveform. So it's going to resist the changes, these fast changes, and it will only go for the average level, which is this here. VAC average. So that's how our circuit works. How are we going for time here? Oh, so here we go. So that's that stage there sorted out. Now, what we need is to implement some of these desirable features. First off, where's our list of things that we want? Right here. First off, we want 12, 24, 36 volts. Well, this board will run on 12, 24, 36 volts by virtue of the fact we're using a 9 volt voltage regulator. Now you may wonder why I've used that and not say a 3-terminal regulator. The quiescent current of a 3-terminal regulator is about 8 milliamps, which is going to be about half of what I hope this thing's going to draw at the end of the day. And it's going to be on pretty much all the time, so we don't want 8 mils. This circuit here will only draw as much as the Zener current. And with a 1k resistor with 12 volts going in, what are we looking at? About a milliamp, just for that alone. So that's good enough. You know, our LED's going to drag a bit, like, you know, another, I don't know, half a mil maybe. But it's no big deal. We've got to keep the current drain of this section down as much as we can, because this is a phantom, insidious current draw. So we've done this. We've got that bit right. I'll tick that off. We don't know yet, so we'll tick that with a question mark. We know we're going to do 1.5 kilowatt or 3 kilowatt. That depends on the output stage and the size of transformer used, but this will run all that, so that's not a problem. Temperature protection. Okay, how have we implemented that? Well, we've got, let's hide that, hang on. We've got a spare gate left out of the 4093, so let's use the spare gate. Let's use the spare gate. So what we have here is a BC547 NPN transistor, which is just biased up with a 4K7 collector load and a very low 1K base resistor, bias resistor, but it's fed to an ordinary 1N4148 diode. Now these things change about, I don't know, millivolt per degree or 2 degrees or something. We don't need accuracy here, we just need to know whether the heat sinks are hot or cold. And if we set this up to trigger at about, I don't know, 100 degrees C, we should be fairly safe. So as that heats up, its leakage current increases or decreases, increases. And because it's in parallel with the base of this transistor, which is on the board, so it's kept cool all the time, as that heats up, it's going to divert current away from the transistor. Yeah, from the base. So therefore it'll turn the transistor. It's alright, I'm tired. I'm not very good at this. As the current through the transistor increases, fuck's sake. I need a whiskey. The current through the transistor is dependent on temperature, and as the diode increases in temperature, it diverts more current away from the base emitter junction of the transistor. And this, once it gets to the switchover point of the CMOS gate, the CMOS will go low. So once this goes high, when that turns on more with the leakage current, it'll turn this transistor off. That'll go high, pulls this point low. This 4K7 resistor here is the open collector current source for our 311 comparator. So obviously when the switch is low, it deprives the 311 of any collector current, so it cannot pulse the main drive circuitry, so it shuts down, and it shuts down in the safe mode as well. As you can see here, we've got to be careful that we don't stop this thing with both, or either phase 1 or phase 2 in a high state, else it'll latch one of the FETs on and it'll destroy itself in double quick time. So that's the beauty of these inverters. If we stop this from triggering, these here automatically will go high, which automatically turns these transistors on, which pulls the collectors low. So both gates on the output stage are going to be low. So there's our temperature sensor, and just for giggles, we've also got a LED that's going to shine and tell you when this part of the circuitry has been triggered. This is a bit cruddy, a bit rough and ready, but it's a simple way of doing it. It's reliable, and as I say, it doesn't have to be, it only has to tell it whether it's too hot, and too hot could be anything 100 degrees or slightly more. So the minute that it happens, it shuts the machine down, and it will stay shut down until the inverter is actually switched off and turned back on again. I'll tell you that works too at some stage. Right, so that's the temperature sensing. Now, what else have we got here? We want our list of things. So, temperature protection, yes. Voltage regulation, okay. Now getting back to this complicated little bit of the circuit here, everything revolves around this LM311 comparator. I've already seen how raising the relative voltage levels of the two inputs changes things. Well, we can actually pulse width modulate a pulse width modulator by changing a DC bias level on one of these inputs. Now ideally, for this to work absolutely technically correct, there should be a virtual earth. I have tried an op amp in here, but I couldn't get it to work properly. So basically all we need to do is lift this voltage sense up and down the same 3 volts. So if we pull that down, for instance, to 3 volts, we'll have no output from the inverter at all, and if we take it up to 6 volts, the limitations of these capacitor voltage levels, we're going to have full power output. So the V-sense only has to vary about 3 volts. We derive the V-sense, it's sitting on 4.5 volts, it's sitting on 4.5, so we want it to go up about 5 volts, so its range is going to be 5 volts to 1.5 pretty much. So we derive this V-sense from our secondary of our transformer. We'll probably just half-wave rectify it to get a sample. We'll get rid of 300 volts of the output signal, which is going to leave us about 10, because we're working with peak voltages with a half-wave rectifier. So then we can process the 10 volts. I'll get into that later on. So voltage regulation, that works, so we can tick that one off. Voltage regulation, tick that one off. True sine wave, well, I'm going to tick that, but I'll show you it on the screen, on the scope. Yes, it uses available parts. At the moment, I don't know about that, but you know, our circuit is certainly coming in under $10. I think it's going to be reliable. We'll find out. Universal, we can tick that one off, because yes, it does. It encompasses different kilowatts, different power outputs, different input voltages, and different mains frequencies. So yeah, I'm going to say it's universal. Overload protection. Now this is really clever. This is 2 components to give it full overload protection. and we look at this inverter, this comparator yet again. Originally I had this here, the output of the comparator connected direct to these two gates, these two inputs. But when you think about it, and let's think about it here, this signal in normal operation of the inverter is a square wave of differing widths depending on what it's doing at the time. But as the load increases, this tends to increase the pulse width, the width of the pulses, in order to try and force more current through the FETs into the prime of the transformer. Now, at full noise, when the inverter just cannot possibly give any more output if it tried, this remains high. There is no pulse width going on, it remains high. Now with a capacitor, it can pass AC current, but it cannot pass DC. So as the pulses get longer and longer and longer, this capacitor eventually will stop giving any pulses, because there's none to give. So these points are pulled low by this 100k resistor, and these outputs just stop pulsing. So the whole inverter shuts down. And the beauty of this is that when the inverter shuts down, the input voltage goes to zero. The output voltage goes immediately to zero. So that the inverter cannot start again, because this voltage, where the hell are we? This V-sense voltage is below the trigger point of the 311. Remember, we've got our 6 volt high trigger, 6 volt low, 6 volt high trigger, 3 volt low trigger. V-sense is actually at zero, so it cannot allow the 311 to trigger the circuit anymore. So we're in a latch state. And this is great, but how do we start it again? Well, again, a bit of cleverness comes to the rescue. We simply have a power on reset. So to reset the inverter, all we're going to do is turn the power off, remove the overload, of course, turn the inverter off, wait a few seconds, turn it back on. We then get this is a power rail here, we then get a voltage spike through this capacitor, which is fed straight into the gates here, which turns these on. A few pulses will get through here, which puts the voltage back onto our V-sense rail, which now puts the 311 into its common mode operating point, and away we go. So that's actually quite clever. I thought, two components, Christ, you can't moan at that, so I'm going to tick that, and it works. I've tried it, it works. So we've got overload protection, we've got 50-60 cycle select, and we can do that by transformer design. So there we go. This video is getting probably a bit long, so what I'll do is I'll come back to you with a working example of this. I've got it on a breadboard, and I can show you the scope traces. Oh, we've also got the last thing I forgot about, we have fan cooling in this. I don't know whether it's going to need it or not, but just in case. So in normal operation, the fan runs at about half speed. We just steal off a 50-50 duty cycle off our division chain here, divider chain, and pulse a transistor on and off, which runs the fan probably about half speed. But when this goes low, under an overload condition or an overtemp condition, this point goes low. We use that basically to short this transistor out, which then turns the fan on flat stick, because obviously it needs to go fast to cool it down quicker if the thing's overheating. So basically, yes, we've got all our criteria met here. I didn't put the fan cooling. Let's 2 speed fan. There we go. So if using this inverter inside, the fan won't drive you nuts. Okay, I'll put all this together and we'll see how we go.